All right, so I'm going to go over 2011 number 5 of that AP packet that I gave out on Monday. So I just kind of broke it down on this piece of paper just to highlight it. Part A says, use the line tangent to the graph of W at t equals 0 to approximate the amount of solid waste at t equals 4. So this t equals 1/4 I'm not going to use until after I've found that my equation of the tangent line, and then I would use that equation of the tangent line to approximate the value. So when they tell me I need to find the line tangent, I know I need to write the equation of a tangent line, which requires a slope and a point. Well, in the given, they told me that at the beginning of 2010, well, that's when my time is 0, that the landfill contained 1,400 tons. So my Y value, and in this case my W value, is 1,400. That's the point I'm going to use because they're saying use the line tangent when t equals 0. The next thing I need to do is find my slope. Well, they tell me that my slope is dw dt is equal to 1/25 times W minus 300. That's my slope. I just need to evaluate it when t is equal to 0 and W is equal to 1,400. Usually we're so used to just taking the x variable and plugging it into this derivative, but we don't have the x variable in the derivative. We have the y variable, which in this case is labeled W. So here to find the slope, we're going to plug in 1/25, and you're going to put in 1,400 minus 300 inside. And so your slope is equal to 1/25 times 1,100, which is 44. So we're going to use that slope and this point to write the equation of the tangent line. So part A, halfway there, equation of the line tangent is represented by y minus 1,400 is equal to 44x minus 0. And again, you could put t instead of x because in this case our x variable's time. So we get y minus 1,400 is equal to 44. I'm going to go ahead and change that to t. I'm going to add the 1,400, and now I have the equation of my tangent line as 44t plus 1,400. And now we're going to use this equation to approximate the value at t equals 1/4. So I'm going to just go ahead and say 44 times, sub in that t value, and you're just going to get y equals 11 plus 1,400. Y equals 1,411. Okay, so that is going to be the approximate amount of solid waste at t equals 4. Again, we could say that that's our W. All right, part B says find the second derivative in terms of W. All right, so we have to I want to bring back implicit differentiation. When we took the derivative and the variables were everywhere, remember we always finished by saying the derivative of that variable with respect to the independent. So here I'm working with dw dt is equal to 1/25 W minus 300. So I go ahead and I just distribute this in, and I get dw dt is equal to 1/25 W minus 1/25 of 300 gives me 12. So now I'm ready to take the derivative, the second derivative, and I get, well, the derivative of 1/25 W is just 1/25, but it's the derivative dw dt, okay, because I just took the derivative of W. So that w went away because remember we drop it by 1, so it was w to the 0, it just turns into 1, but we have to finish saying the derivative of w with respect to t. Okay, and then this minus 12 just turns into 0. So again, they're saying, right, find the second derivative in terms of w. So we got dw, the second derivative, is equal to 1 over 25. Well, we know what dw dt is. It was, going back to the very beginning, 1 over 25 w minus 300. So my second derivative, cleaned up, 25 times 25 is 625 w minus 300. And that's my second derivative. Now they went on to ask me to determine whether my answer in part A is an underestimate or an overestimate on the amount of solid waste that the landfill contains at t equals 1/4. Okay, so remember when we're talking about underestimating, overestimating, it's all based on the concavity. We talked about this earlier. If I have a function that's concave up, then my line tangent's going to, no matter where it is going to lie below. So a concave up, which means that a second derivative being positive, means that it's going to be an underestimate, the tangent line. And then vice versa, if I have a concave down scenario, that tangent line, no matter where I draw it along that curve, is going to lie above. So a concave down means that my second derivative is negative. And so then if that's the case, it would be an overestimate. And in order for you to justify, you must relate the problem to the second derivative and its concavity. So they're asking me at t equals 1/4. Well, there was a couple of important information that they said in the very beginning of this problem. They said that the increasing function, okay, so that means that my the output's getting bigger, so my W is getting larger from 1400. 1400 should be the smallest. So if I try to estimate what the second derivative is, I know at 1/4, at t equals 1/4, well, I know at t equals 0, this is 1400. I know this number theoretically should be bigger than 1400. And again, I don't really care about my number, I care about my sign. My second derivative here would end up being positive. So I could say my second derivative is greater than 0, therefore it is concave up, and so the tangent line at t equals 1/4 is an underestimate. And when I collected your homework, I saw that some of you guys had that incorrect. You had the right concavity, but you said that it was overestimate. If it's concave up, it's an underestimate. Okay, last part. It says, find the particular solution of W equals WT to the differential equation. So this is just what we've been doing, that we have to separate and integrate, and we have to apply the initial condition to find C. But again, we're going to we'll do it together. W 1 over 25, W minus 300. Okay, so first step, always separate those variables. I get dW is equal to 1 over 25, W minus 300 dt. So dt tells me only my t variables can be on this side. On this side, we can only have W. So we're going to move this over by dividing W minus 300, that binomial, over. And we get 1 over W minus 300 dW is equal to 1 over 25 dt. Okay. Now I'm just going to bring this binomial up so that I have it in the form that I can integrate. All right, you guys should be getting to be pros at this. So when I do this, I see that -1 exponent. That tells me it's an ln problem. I double check that it's going to be a straight sub-in. So if my u would be w minus 300, and my du would be dw. So this can go straight into ln of u, which is w minus 300, plus c is equal to 1 over 25t plus c. And then I want to minus that c over. I'm trying to solve for that differential, that particular solution. So I just want to get 1c, and now I did. And I'm here, this is considered my general solution. Once I have my general solution, I plug in my initial condition. My initial condition is 0, 1400. So ln, that's my w's, 1400 minus 300 is equal to 1 over 25 times 0 plus c. So I get that c is equal to ln of 14, whoops, I'm going to clean that up. I'm just going to say of 1100. Okay, so now at this point, I plug into my general solution. ln of w minus 300 is equal to 1 over 25t plus ln of 1100. All right, so now I need to get to w. So this is, I got to get it out of that Lagrange, so I need to change it to exponential form. So I'm going to get that e, this is the exponent, I should get this as my exponential form, 1 over 25t plus ln of 1100. And then we know that if it's being added, the exponent's the same thing, 1 over 25, as it being multiplied with the same base. And I like that because then I'm able to get rid of this e the ln, and this comes down 1100. So I get w minus 300 is equal to 1100 e to the 1 over 25t, and last but not least, I add the 300. And we've always been looking about, do I need a specific domain? And here, I know that they had told me that this was good for the first 20 years. So it's going to be for t is equal to 0 to 20 would be my domain. And that's the solution. All right, hopefully that helped.